Hi everyone, my name is Matt Tobin, and today we're going to be talking about demystifying fusion and other miscellaneous associated topics with fusion that relate to the topics that we've covered earlier in the series. So these are the six topics that we'll cover today. First, we'll talk about cold fusion and bubble fusion, which you might have heard about previously in other contexts. We'll also talk about actually connecting fusion power plants to the grid. We'll talk about the systems that support fusion devices beyond the systems that we've already talked about to date. We'll also talk about fusion fuel cycles and then other fusion research that's going on. So there are kind of three um, different varieties of cold fusion research, and we'll talk about each of these three different versions in turn. The first cold fusion research is related to submerging electrodes in deuterated water. So what do we know about fusion so far? So the triple product is the quantity that we use to describe how close a fusion reaction is to actually producing energy from reactions. So we need to achieve above a certain triple product in order to actually make fusion viable. So this means that we need to have a dense plasma, that's the N in the NT tau, the triple product. We need to have a hot material, so that's the capital T in the triple product, and then we need to confine things for a long enough time to allow enough fusion reactions to take place in order to get a feasible fusion reactor. So typically, as we've talked about throughout this course, in magnetic confinement fusion, this is approached by creating a magnetic bottle, a tokamak in most cases, that confines very hot matter in the form of a plasma, heats it up, and allows fusion reactions to take place. But there has been a lot of focus on or desire to pursue potential methods to make fusion reactions happen at scale at room temperatures, which, for reasons that should be clear at this point, has a lot of advantages because it means that we can obviate a lot of the systems that support making an actual tokamak. So the claim of this approach to cold fusion is that deuterium absorbed in a metal catalyst can actually allow fusion to occur between these deuterium atoms or nuclei without the application of external heat or compression, as would be the case in magnetic confinement fusion or inertial confinement fusion. And this is because there are various electrochemical and quantum effects that take place when the deuterium is embedded in the metal that allow us to sidestep the Coulomb repulsion, the Coulomb barrier that keeps the deuterium nuclei far apart and prevents them from fusing otherwise. There was an infamous study published by Fleischmann and Pons in 1989 that claimed to have discovered this effect or found evidence that it was working. However, there were conflicting results between these scientists and those who tried to reproduce or confirm their work. And in general, this study is considers to not be valid. The evidence is seen as weak or potentially an artifact of poor data analysis or diagnosis. So these initial kind of experiments that were published seem to have been plagued by measurement errors. Again, no other research labs could really reproduce the results, and it is generally in the field considered a closed question that this approach probably does not actually yield viable fusion energy. But there are still some scientists who consider this possibility and are looking at other similar approaches. And one of those approaches is called lattice confinement fusion. So actually, there's a NASA research team working on lattice confinement fusion. The idea behind this approach to cold or room temperature fusion is that when deuterium is embedded in a metal lattice, there are certain processes that you can induce through irradiating that metal with gamma radiation to produce the conditions locally for high energy deuterium nuclei to collide with each other and fuse and produce energy from fusion. So this approach has been shown to produce fusion neutrons. It's also been shown to induce nuclear fission in the metal itself. And the link on this page connects and the link on this page shows the results from the NASA scientists, which is actually being used currently as a neutron source. The scale of this research at present is not large enough to actually be applicable to a fusion power plant, but there is research going on to try to scale up this approach to make it to those relevant conditions. There are other groups also outside of NASA working on lattice confinement fusion. Recently in Nature, there was a This paper published looking at the electrochemical loading enhancement to deuterium fusion rates in a metal target. In this case, a deuterium plasma is actually used to embed deuterium in a metal target, and increased fusion reaction rates from electrochemical effects were also observed. So again, this kind of scale of this research is relatively small, currently not at the same level of the scale of research of, for example, tokamaks or inertial confinement fusion, but still, interesting to observe these different secondary effects and smaller effects that can improve fusion rates at room temperature. Another kind of weird approach to fusion at room temperature is called bubble fusion or sauna fusion. So again, based on kind of what we know about fusion so far, is that we need to have our material dense, hot enough, and confined for a long enough time in order to make fusion happen. And the claim in bubble fusion or sauna fusion is that the cavitation of bubbles, so bubbles forming in a liquid and then collapsing in on themselves, can actually create the conditions necessary for fusion to occur. So we talked about how in inertial confinement fusion, we use lasers to compress the target fuel in order to produce fusion relevant conditions. In bubble fusion, the idea is that the cavitation of bubbles in a deuterated liquid can actually produce similarly relevant temperatures for fusion and allow fusion to occur. So there's some conflicting results between scientists on this subject. A lot of similar to the approaches to cold fusion in the past. The results from these scientists have kind of been hard to reproduce, and there are a lot of questions about whether or not we're actually observing fusion in these cases or not. However, it is kind of still a mystery why, when we see cavitation of these bubbles in these liquids, light is produced. So that's one of the kind of primary pieces of evidence that has been used to support the hypothesis that fusion is occurring in the cavitation of these bubbles. So that's still not really widely understood, and research is still being conducted to better understand that. But in general, we don't consider this a viable approach to fusion, especially at scale. So that covers cold fusion and bubble fusion, these kind of smaller side approaches to researching fusion that are done on smaller scales. We'll talk now about fusion on the grid. So how we actually take the tokamaks and cellars that we've talked about throughout this course and how we can connect those to the electricity grid. So we've talked mostly about what's happening in this gray sphere of the fusion power plant, but there are a lot of processes that go on after the actual fusion produces energy to take that energy, turn it into electricity, and then connect it to the grid where a bunch of people can use it. So what do we mean when we say the grid? So the power grid is this huge network of generation and use and conversion facilities throughout the United States and throughout the world, in fact, where energy is created, shared or distributed, and then consumed. And the different nodes in this network are operated and overseen by different groups, different authorities, who then all have to work in coordination with each other in order to make sure that you and I don't notice any kind of disruptions in our electricity service or unreliability otherwise. So this grid is supported by generation facilities throughout the country. This map produced by Weber State University indicates the many different power plants that exist throughout the United States. So you can see based on the different color and size of these different dots across this map, how the electricity is generated in different regions and how much electricity is generated based on the size of the dot in these different areas. So you can see in the middle of the country, there are a lot of lighter blue dots indicating there's a lot of wind power generation in these areas. You can see in the Pacific Northwest, there's a lot more hydropower. And along the East Coast, especially, there's more traditional fossil fuel generation, so gas, oil, etc. If we take a zoom out, if we take a step backwards and look at kind of the global generation, much of the electricity in the world is generated by more traditional, especially fossil fuel driven approaches to electricity generation. So coal, oil, and gas typically. And you can see at the very top of this graph, a small but growing proportion of that energy generated globally is produced by more sustainable methods, so nuclear fission, solar and wind energy, etc. If we look at the US specifically, this is an example of the electricity generation in 1 week. And you can see the breakdown of the different electricity sources. So you can see at the bottom of this graph, there is nuclear fission, which produces what's called the base load electricity, natural gas, which also contributes to the base load, but then can be modulated in order to backfill when there are periods of higher demand or lower production on other energy sources. There's also coal, hydro, and then renewables like solar and wind, which are much more subject to weather conditions and day-to-day, hour-to-hour variation. And the more baseline loads and peaker loads can backfill vicissitudes, changes in the production from solar and wind. We can actually see these changes over the course of a day in how much electricity is being generated. If we look at the frequency of the alternating current that comes to the outlets and et cetera in our homes. So if we look at the frequency plotted versus time, typically the frequency stays around 60 hertz, oscillating back and forth, but that frequency isn't straight or isn't flat. There are actually, periods of time when it increases or decreases. And that frequency depends on the electricity generation that's occurring on the grid. Ideally, we'd keep the frequency right at 60, but again, in order to account for all the different sources of generation and of consumption on the network, there are slight variations hour to hour. This graph shows an example of a kind of more severe event in which there were several outages that shut down a large portion of production that caused the frequency to drop to a very low level, as you can see by the red valley in this graph. And when that occurred, additional electricity generation plants were started up in order to compensate for that and bring the frequency back into a normal operating range. And you can see this graph, this parabola plotted on the other side of this slide, showing that there's kind of an acceptable range around the base frequency that we accept the electricity to be delivered at. And if we start to move outside of that band of acceptable frequencies, we need to compensate by either increasing electricity production on those power plants that have a variable production amount, or turning off or decreasing the electricity generation. So if we look at just kind of the power plant level, what's happening at each of these individual plants that were shown on the map a few slides ago, typically we have some source of heat. So in this power plant, for example, we have coal that's burned, and that heat turns water into steam. Once you have steam, that steam can then be used to turn a turbine. That turbine turns an electric generator that produces electricity from the mechanical motion of the generator, which then is delivered to the transmission lines. Ideally, in fusion, what we do is we remove this coal section of this power plant, this coal burning section, and replace it with a tokamak or accelerator or some other, concept for fusion reactions. And contrary or unlike hydropower or wind or solar, power plants that use fusion can largely be replaced kind of exactly where gas and coal power plants are right now. The renewables like wind power, solar power, often require very specific sightings, kind of larger distributed generation networks that make it harder to plug them into existing infrastructure. But fusion is very well suited for the coal, gas, and oil-dominated power plants that we have today. And that's generally the picture of how we'll take a fusion power plant and connect it to the grid to make electricity. If we look more in depth on the side before we connected the transmission lines, the fusion core, which is where the fusion reactions are happening, for example, in a tokamak, will produce energy that can either go to thermal storage, so heating up a material that we can then use later to produce electricity, or directly to power conversion. And that power conversion will then connect to the grid to deliver energy. If you look at the sub figure B here, Typically, a fusion power plant, will operate for a period of time and then have a downtime, either because it's a pulse reactor or because we'll have some time that we'll need to produce or to maintain the reactor, to go in and fix things that might have broken, etc. So when that happens, obviously the energy delivered drops. Typically, because we're doing a thermal cycle, it doesn't drop fully to zero. And then once we turn the fusion power plant back on, the electricity, the energy that we're delivering jumps back up. And that's what you can see depicted in the top graph B. You can also see a difference in the actual fusion power, the amount of energy that's being delivered by the core, and in gray, the actual gross electric power that's delivered by the power plant. And we'll talk about those differences and why there's a discrepancy between the actual energy produced by the fusion core and the amount of electricity that we get delivered to the grid. So that's the power generated. That's what's coming out of your power plant. And then you also have electricity that you need to actually run your power plant. So electricity that goes into your tokamak or your stellarator or whatever. And that's what's depicted in subfigure C on the slide. So you can see that there are in blue some sources of active recirculating power that are needed when we turn the fusion power plant on. So this could be running the magnets, running the heating systems, etc., for actually making the power plant work. There are also passive components to the recirculating power. These are things like keeping the lights on, keeping the cryo plant on, which doesn't turn off when the fusion reaction is stopped, when we need to do maintenance or things like that. So those are the two main components of the recirculating power in a fusion power plant. There's also a significant amount of energy that's required when we actually start up a power plant, either at the beginning of its life or periodically, after downtimes for maintenance and things. And that's what's depicted in purple in subfigure C, showing that there's a large amount of energy for a short period of time that we need to start up the power plant, and then we can recover that based on the electricity that we generate from the fusion reactions over the course of the time that it's on. So how do we account for the discrepancies between the amount of fusion power that we actually produce in the core and the amount of electricity that we get out of a fusion power plant? So this pink box shows the amount of energy that is actually produced by the plasma, or P fusion. That energy gets put into both neutrons, which stream out of the reactor and are our primary source of electricity, or how we make usable energy from our fusion reactor. But there are also alpha particles, so helium nuclei, that are produced from the fusion reaction that also take some of this energy, which then stays in the plasma. Those don't get emitted and turned into electricity in the way that we do neutrons. So that kind of reduces the amount of energy right off the bat that we can use to make electricity. Those neutrons that stream out of our reactor get embedded in what's called the blanket around the plasma core, and those neutrons then heat up that blanket, and that heat can then get converted into electricity. Not only do they heat up the blanket by depositing their kinetic energy into it, but they also can induce fission of the material in the blanket that can produce even further heat. So that's why the box labeled blanket and exothermic reactions is slightly bigger than the box labeled neutrons, because there's actually a slight multiplication factor of the energy that gets deposited in the blanket from the fusion reaction. From there, we actually do the energy conversion to electricity. And unfortunately, that process is very inefficient. So you can see that where we break off into the green electrical power arrow, there's a significant conversion loss due to the process of actually turning our heat energy into electricity. In addition to that conversion loss, there are the recirculating components of the power that I mentioned on the previous slide. So the power that we need for the heating systems, the magnets, cryoplant, etc., that we siphon out of the electric power that we generate from the power plant. Also, power for heating and current drive in the plasma that has its own efficiency associated with it when we convert it from electricity into the energy forms that we actually put into the plasma. So the amount of electric power that we actually then deliver to the grid is, a fraction of the amount of power that we actually produce from the fusion reactions in the plasma. And that's what's depicted in the green arrow at the bottom left of this slide. So again, looking at this graph of the different sources of energy and how they vary throughout a typical week, we can identify kind of different characteristics of these different sources of energy. So there are peaking units that can respond quickly to changes in demand and changes in supply. These can operate, either for a short period of time or at variable power output. So a natural gas turbine power plant is kind of one example of those. There are also intermediate units that we can moderate somewhat, depending again on the demand and supply. And these include a combined cycle gas plant and a medium-sized coal plant. Then there are baseload units. These ones are much harder to throttle, so they typically just produce a set amount of energy constantly over time. And these include nuclear fission power plants and larger coal power plants. There are also storage units, so generally, kind of some form of battery, hydrogen burners, hydroelectric power plants that store power in some form, and then those can then output that energy as electricity as needed. So where does fusion fit into this picture? We generally imagine it fitting into somewhere in between intermediate units and base load units. So fusion power plants will generally deliver some base load, but they can also produce a slightly variable amount of power that we can use to respond to, again, changes in demand or supply. There's a lot of focus in the fusion community about trying to replace natural gas. So natural gas, especially by energy companies, is often billed as a relatively clean source of energy. And if we compare it to oil, coal, wood, as you can see in this graph, natural gas does produce much less carbon dioxide per kilowatt hour. So it is relatively clean compared to these dirtier forms of energy. However, it's still much dirtier than renewables or fusion would be. And we can identify that by some of these facts from the Energy Information Administration and the Rocky Mountain Institute. So natural gas actually makes up about 35% of the energy-related US carbon dioxide emissions, so a very significant portion of those emissions that are going to warm the atmosphere. Ignoring carbon dioxide for a minute, if we think about methane, methane emissions from natural gas power plants are actually 80 times more damaging than carbon dioxide and are a major source of pollution and climate warming greenhouse gases. So we also need to consider not just the carbon dioxide, but also the methane emissions from these sources when we're comparing them against other potentially alternative electricity generation methods. There's also an estimate from the Rocky Mountain Institute that the damage from methane leaks alone might be equal to the total environmental damage from coal burning taken all together. So this indicates, again, that even if you think that natural gas might be slightly cleaner, just looking at the CO2 emissions, there are actually other effects of natural gas that can be much more damaging and motivate looking for alternatives to using natural gas, both for base load electricity generation and for peaker or alternating kind of variable power output electricity sources. So some work has been done in order to better understand how fusion would actually economically fit into the grid. And we can see that looking at these graphs, fusion shown in the pink in these bar charts produces more or less a baseload amount of energy that can support the electricity demand of the networks to which it's connected. But then in periods of the day or of the week in which solar power and wind power can produce more electricity, we can throttle down the fusion power plants in order to allow those electricity generation sources to serve more of the grid. So this is kind of one vision for how a more sustainable electricity grid might look with fusion integrated into the mix. So that covers how fusion will be connected to the grid and where it fits into the energy ecosystem. Now we'll talk a little bit more about the details of a fusion device beyond the components that we've covered in more detail in this course, because the fusion plants that we're envisioning are much more complex than we might have let on. Oftentimes, people ask, what are all the parts of a fusion reactor? And we've shown throughout this course some more simplified pictures of a fusion reactor, showing, the central solenoid, the magnetic field coils, and they typically look something like this. So you have the center stack or central solenoid that drives the current toroidally in the plasma. You have the toroidal magnetic field coils that create the donut-shaped magnetic field, and then poloidal field coils that turn the plasma from being a circular cross-section into a more elongated cross-section and can control the position. if we compare that kind of simplified picture to a cross-section of the ITER tokamak that's being constructed in France, we can see that there are all these other subsystems that support it. So we've been focusing kind of on this core area of the plasma towards the middle, but there are all these subsystems surrounding that core that are needed to support the fusion power plant. Looking first at the central solenoid, for example, we know that that central solenoid, as we've discussed, is used to drive current in the plasma, which improves the confinement. It's also used to heat the plasma, somewhat like a transformer. So if you've ever taken an E&M class, you know that a transformer takes the current running through one loop of wire and can drive a current in another loop of wire called the secondary. And in the case of a fusion power plant, that secondary is the plasma itself. So that kind of transformer effect is what's used to drive the toroidal current that keeps the plasma confined and also heat it up. Just taking a look at some of the central solenoids from tokamaks around the world that are actually being constructed, you can see some examples here. These components are sometimes difficult to maintain, and for that reason, we'd like to rely slightly less on them for running a tokamak. This graph shows the contribution of the kind of power input to a tokamak over time, and you can see that for hotter plasmas, the amount of energy that we can actually put in through the central solenoid gets lower and lower and lower. And we need other sources of energy in order to heat up the plasma to achieve fusion-relevant conditions to get high enough NT-tau in order to make fusion reactions happen. So how are we actually going to achieve that? How are we going to put in enough power for enough time and once we get a hot enough plasma to make a fusion reaction happen? Overall, this boils down to the idea that we need kind of some options for heating up the plasma beyond startup. One of those options is neutral beams. In a neutral beam, basically what we do is we use a particle accelerator to heat up fuel atoms, so that's hydrogen, can be deuterium or tritium, up to high energies. We then neutralize those charged particles and then inject them into the plasma such that they can traverse the magnetic field and deposit the high energy fuel deep into the core of the plasma. One of the drawbacks of neutral beams is the fact that they require a direct line of sight into the tokamak or stellarator, whatever fuel or whatever fusion device you're considering. These are the parts of a typical neutral beam. You can see that there's a bellows that connects to the vacuum vessel of the fusion reactor, a calorimeter, an ion dump, neutralizer, that is where the charged particles with high energy are converted to neutral particles, an accelerator grid, and an ion source that is the actual source of the fuel. Again, these devices need a direct line of sight into the plasma, so are typically not being considered for neutronic fusion power plant approaches because neutrons emitted by the plasma can backstream and damage the neutral beam itself. So an alternative to neutral beams for heating the plasma is microwave heating or in general radio frequency heating. And in these devices, we take launched radio frequency waves that can be absorbed near the cyclotron resonance or other resonances in the plasma in order to selectively heat different species, so electrons or ions or other species in the plasma. We can also, because we know the magnetic field in the plasma with relatively high precision, choose a specific position in order to deposit this energy. And based on the way that we direct the energy, we can use it either for purely heating or even driving current in the plasma. So this is a common approach to heating up and driving current in a plasma after the startup has happened and after the central solenoid or ohmic heating coil is no longer active. One of the drawbacks of using this radio frequency heating approach is that if a plasma is too dense, the waves that we project at the plasma can be reflected and not penetrate into the core of the plasma where we actually want them to deposit their energy. In a previous lecture, we talked about how in the ionosphere, we can actually bounce radio waves off of the plasma surrounding the Earth, and that can be used to improve communication here on Earth. This is a similar physics, but it's deleterious to the goal this time of actually penetrating the plasma and heating it up. This is more of a problem on spherical tokamaks and accelerators, but it's also projected to become an issue on larger tokamaks in the future as well. So if we put this together, we can see that there are kind of several methods that we have, several levers that we have for driving current and heating up the plasma. This is a depiction of the ITER heating system. You can see there are several ECRH or electron cyclotron resonance heating systems and also neutral beam injectors in order to drive current and heat up the plasma. So those are the heating systems that support the actual tokamak. What are the other components that make up this large device and can actually turn the basic tokamak that we've been talking about into a power plant? One of those is the diverter. So the diverter is the area of the tokamak or whatever your device is where the magnetic field lines actually terminate on or touch the wall. And these are places where the hot plasma kind of comes into closest contact with the typically solid material that surrounds your plasma. Because of this, there are high thermal and radiation and even particle loads on this part of the device. So there is a significant amount of armor and cooling that's needed in order to protect the diverter and make it so that the tokamak can actually run. These areas can also be used to extract ash and other contaminants from the chamber. They can also be used for fueling and for the fuel cycle, as we'll talk about a little bit later. Nowadays, most of them are made out of high melting point metals. So tungsten is a common one. But there's a lot of material science research going into exploring other materials that can be used to replace those that are in use currently. So silicon carbide is one. There are actually studies looking at using liquid diverters. So rather than using a solid material interfacing with the plasma, using a liquid that might be more resilient to damage from the incident plasma. In addition to the diverter, we have the blanket that surrounds the tokamak. This is the component that actually absorbs all the neutrons that come out of the fusion reactions. And it's where that neutron energy is then converted to heat, which drives the thermal cycle that is converting our fusion energy into electricity. In future power plants, this component will be extremely important, and we have a lot of different uh, uh, constraints on the materials that we can use for it. So we need to have a material that will absorb neutrons well. It needs to have a high boiling point so that it can be a working fluid for us in the fusion reactor. It needs to have good thermal cycling characteristics for the thermal cycle that we conduct to convert the fusion energy to electricity. It's also going to be bombarded with a ton of neutrons, so we need to have low activation characteristics. And there are a lot of other requirements that go into selecting a neutron material and neutron breeding blanket design that then surrounds the power plant. There's a lot of research being conducted right now on the material side, especially to better understand what possibilities we have for the breeder blanket. And that covers the kind of primary components of a tokamak that we have not talked about to date in this course. We've talked a little bit about just now when touching on the neutrons and the diverter, we've talked a little bit about the fuel cycle and how we actually put in the reactants in our fusion reactor and get the products out. So we'll talk now about fusion fuel cycles and the practical aspects of that. So our fusion chamber, which can be a tokamak, it can be an inertial confinement device, it can be a stellarator. Regardless of what the actual fusion chamber is that we use, we have all of these systems that kind of surround that device in order to support the fueling and conversion of fuel into products and management of those reactants and products. And this diagram depicts kind of some of the subsystems that go into maintaining that fuel cycle system. So throughout this course, we've talked mostly about the DT or deuterium tritium fuel cycle for fusion reactors. Let's focus a little bit on the T or tritium in that reaction. So tritium is an isotope of hydrogen, much like deuterium. It consists of a proton and two neutrons. It also exists relative to deuterium in relatively low abundance. And this is because it's slightly radioactive. It has a half-life of 12.33 years. Because of this, it's very expensive. So currently about $33,000 per gram and rising. Why do we consider tritium when it's so sparse, so hard to come by? The reason is because deuterium tritium fusion is the easiest fuel cycle to achieve net energy. So if we look at the total reactivity in this plot of some of the easiest fuel cycles to consider for fusion, we see that deuterium tritium fusion peaks at a lower ion temperature and peaks at a higher reactivity. So this means that we can get kind of more fusion happening at lower temperatures compared to other fuel cycles. It's essentially the lowest hanging fruit in the fusion ecosystem. So deuterium tritium produces high energy neutrons from its reaction, as we've talked about throughout this presentation and this series. And because of that, we can use those neutrons in order to produce electricity. Unfortunately, those neutrons also activate the materials in the fusion power plant, and we need to have systems to deal with that, and it limits the life of the power plant. But it's kind of a double-edged sword in that we can produce electricity from them. Also, like other forms of hydrogen, tritium permeates deeply into many metals. This is a problem because tritium is expensive, it's radioactive, and this process also degrades the metals that the tritium permeates into. These are kind of the drawbacks and benefits of using tritium as the fuel source. Where do we actually get tritium from? So it's produced currently in most CANDU fission reactors. These are Canadian heavy water reactors. You can see a picture of one here and then also a diagram of a typical fission power plant. So these reactors typically produce about 130 grams of tritium per year. If we consider a demo-like reactor, so a prototype fusion reactor, we're going to need about 300 grams per day of tritium in order to produce energy at scale. So clearly we need to figure out kind of some other way in order to produce tritium. If we consider the global supply of tritium right now, we only have about 20 kilograms in existence. So we need to, again, figure out other ways in order to drive up the supply. So how do we do that? The idea is to actually make tritium inside of our reactor using the neutrons that come out of our fission reaction. So at the left of this slide, you can see the DT fusion reaction that happens in the core of our reactor. The neutron that comes out of that reaction, though, which again is not confined by the magnetic fields and is captured by the breeding blanket that we've talked about earlier in this presentation, can then be used to produce tritium in a fission reaction in the breeder blanket. So you can see that when in the reaction on the right, when a high energy neutron comes in and impacts a lithium nucleus, that lithium nucleus can actually fission, break up into helium and tritium, and that tritium we can recover and put back into our fusion reactor and use it as fuel. In this way, for a fusion reactor, we only need a smaller amount of startup tritium in order to get the reaction going, and then we can use lithium to produce the fuel that we need to keep the reactor running for years to come. So this slide shows some of the candidate breeding materials that are going to be used or that we're considering using in the neutron breeding blanket surrounding the tokamak. So there are liquid metals like lithium or lead lithium, solid ceramics that contain lithium, and also molten salts such as FLiBe that we're considering kind of flowing around the tokamak reactor to capture the neutrons and turn their energy into electricity and also convert lithium into tritium. There are some benefits and drawbacks to each. In liquid metals, there are challenges to the stability and also the material handling. In solid ceramics, there's a lot more research that needs to be done to understand how to use them, and also a lot more infrastructure in the actual plant needed in order to make them viable for lithium breeding. And then there's also drawbacks to molten salts. They're highly corrosive, also have high melting temperatures, but currently, because of their thermal properties and because of how much they've been studied, are the primary approach that we're considering for breeder blankets in fusion reactors. So, in order to actually convert the neutrons into the tritium that we need, and produce enough tritium in order to sustain the reaction, we need to have a high TBR, or tritium breeding ratio. Typically, to account for inefficiencies in the system, we need a TBR of greater than 1.1 in order to keep the reactor going. Again, they're kind of different materials with different TBRs, different blanket designs that are under consideration. One possibility to improve the TBR is to use enriched lithium, so selectively incorporating lithium of different isotopes of lithium in order to improve the likelihood that the neutron impacting the lithium will fission the nucleus into tritium. Will potentially be necessary in kind of different blanket designs. So that's how we actually get the tritium, get some of the fuel to put into the reactor. Deuterium, the other half of the DT reaction, is relatively easy to harvest, even from seawater. So in terms of getting that side of the reactants, it's relatively straightforward. How do we actually get that fuel into the reactor, though? So typically nowadays, we simply inject gas into the reaction chamber. It's relatively simple to do this. However, there is trouble with that gas then penetrating deeper into the core of the plasma and depositing the deuterium or tritium into an area where most of the fusion reactions are happening. So the kind of alternative that's currently being studied and has been implemented on some devices is cryogenic pellet injection. So in cryogenic pellet injection, we actually take these forms of hydrogen, deuterium, and tritium, which are typically gases, at room temperature, cool them down to solid state, and inject them into the plasma such that they can cross the magnetic field lines and deposit their fuel into the core of the plasma. This allows us to tune where that fuel gets deposited, and can be much more effective, much more efficient than just puffing gas in from the edges of the plasma. So this is kind of the approach that's envisioned in the future for fueling fusion reactor. In addition to putting that fuel in, we also don't burn all of the fuel. We don't have perfect efficiency for burning the fuel that we put into the reactor. So we do need to extract the unused fuel, separate it, and then reintroduce it into the machine as possible to keep the fusion reactor going. As you can see depicted in this diagram, there is typically a tritium plant that's used for conducting this process. And it's envisioned that in the diverter region, which we talked about earlier in this presentation, is where you'll have the exhaust extraction, where you can take the unused fuels, again, separate them, and then reintroduce them into the reaction to keep the fusion reaction going. And that pretty much covers the kind of broad strokes of the fusion fuel cycle. So again, there are all of these subsystems that are needed to support the actual running of the fusion reactor, extracting the fuels and putting them into the reactor, and keeping the plant running. And with that, we'll talk quickly about other fusion research that's going on. So we've talked a little bit about inertial confinement research, a little bit of history on ICF. So ICF was initially considered as a way to study and improve thermonuclear weapons. This was in response to the Partial Test Ban Treaty of 1963, and it became the only way to kind of directly observe the conditions that occur at the detonation of an atomic explosion. So much of the inertial confinement research is directed towards the stockpile stewardship program, and it's classified and related to national security. Inertial confinement devices, though, are really interesting scientific tools that have a lot of relevant science that they produce, relevant findings that they produce, that help us better understand the subsystems and components of a magnetic confinement fusion device. For example, at the National Munitions Facility, when there are inertial confinement fusion experiments conducted, we can better understand how the material behaves when it's in those conditions. We can also conduct neutronics research, so better understand how the reactants, once they turn into a neutron and helium, then impact the materials surrounding the fusion reaction, and a lot more interesting physics, so we can better understand the conditions in supernovae and kind of other interesting topics related to high energy physics. There's also what's called magnetic target inertial confinement fusion. So the Z machine at Sandia National Labs is one example of a facility looking at this approach to fusion. Again, it's harder to envision scaling these approaches to an actual fusion power plant, but there have been a lot of interesting findings from the scientific research that goes on in these facilities. So better understanding the unique phases of matter that occur in these conditions, investigating shock waves in materials and in plasmas, and a lot more kind of basic physics knowledge that is discovered at these facilities. So that covers kind of the kind of miscellaneous topics that we haven't yet discussed in this course, but think are important to touch on in a course on fusion energy. I'll talk now a little bit about what fusion is like as a student, from my perspective in the Columbia Plasma Physics Lab. So there's a lot of interesting physics that goes on that we've talked about kind of at the high level through this course. But in terms of what research an actual student does, it's typically a very small portion of that bigger picture. So we've talked a little bit about disruptions in tokamaks. My research is on how to predict and avoid when disruptions, typically caused by instabilities in a plasma, are going to occur. And my work focuses on the real-time assessment of that plasma stability and implementing control approaches to avoid vertical displacement events. As a student, I've been lucky enough to travel to different places around the world in order to implement this research and collaborate with other folks in the field. And again, even though I am not personally building a tokamak reactor, I and a lot of the other students in this lab are working on small parts of the puzzle, small pieces of the puzzle, to support the overall goal of building a fusion power plant. That brings us to the end of this series of lectures about fusion energy. On behalf of the Columbia Plasma Physics Laboratory and all the students who participated in putting together these slides, we hope that you found them informative and interesting. Thank you so much for following along.